Hey, Global Impact students, this is Mr. Ellinger here, and this lesson is on systems with three variables, systems of equations with three variables. Our learning targets for this lesson is we want to be able to solve systems in three variables using elimination, and also we want to be able to solve systems in three variables using substitution. Our essential understanding for the lesson: systems of three equations and three variables can be solved using some of the same algebraic methods used to solve systems of two equations and two variables. If the equations of two systems are equivalent, then a solution of the system that is easier to solve is also a solution of the more difficult system. So some background for this lesson: we will use the same algebraic methods as two variable systems to solve these three variable systems. The solution of a two-variable system can be represented as the intersection of two lines in the coordinate plane. The solution of a three-variable system can be represented as the intersection of planes in a coordinate space. So we're talking about a 3D graph space here. Graphing is not an easy or practical method for solving three-variable systems, so we will use algebraic techniques. This lesson is going to show you what a system looks like in 3D space. To solve systems of three equations in three variables, you can use some of the same algebraic methods you use to solve systems of two equations in two variables. You can represent systems of equations in three variables as graphs in three dimensions. The graph of an equation of the form ax plus by plus c z equals d, where a, b, and c are all not zero, is a plane. You can show the solutions of a three-variable system graphically as the intersection of planes. So here I have an illustration of some different scenarios involving three planes, and these are difficult at times, especially initially, to kind of grasp here because we're looking at a two-dimensional representation of something that's three-dimensional. So, again, we have 1, 2, 3, 4, 5. We have 5 different scenarios of the intersection of three planes. Okay. So this first scenario here, we just have each individual intersection is just the intersection of two planes. This one in the middle, we have two planes intersecting one plane. Down here in the bottom left, we have two planes intersecting in a line, and then a third plane intersecting those two intersecting planes, and their intersection is a point. And then over here on the right, we have three parallel planes. And then down here in the bottom right, we have three planes that all intersect at a line. Okay, so the top three here are all examples of no solution to a system of three variables, three equations. And this bottom left one is an example of one solution, so there's a single point where those three planes all intersect. And then the bottom right is an example of an infinite number of solutions. Planes intersect at all the points along a common line. So what I'm going to show you right now is just what it looks like to graph in 3D space. And like I said, it's a little bit different. All the graphing that you've done up to this point is all two-dimensional, an XY plane on a flat surface. The easiest way to imagine this is if there was another axis coming out of your page, okay, running perpendicular to your page, going through the origin. We call that the z-axis. So let me show you what this looks like, and then we'll pick back up the lesson. Okay, so I'm going to show you guys an animation here that gives you some idea of what it looks like to graph a point in three dimensions. And it's a little strange, it's a little weird. We kind of have to use our imagination quite a bit because, again, we're working on a two-dimensional surface, so we have to try to bring in this third dimension. And what we do is, normally, like the picture of the graph that you're looking at right now is pretty standard. We got the y-axis running vertically on our page. We have the x-axis running horizontally on our page. But like I mentioned before, there is a third axis that we can insert here. And as you're seeing it right now, that z-axis would be running perpendicular to this plane, this xy plane, going through the origin of the two axes. So what we're going to do is we're going to kind of change our perspective in the graph here. And one of the ways that we do this is we're going to drop our y-axis flat. Okay? So after I drop this y-axis flat, you see the y-axis is now running kind of diagonally across the page. The x-axis is still running horizontally in reference to the actual page. So we have a you can see how these labels are. You can think of this as you're holding a piece of paper out in front of you, and that would be the x-y axis, and the z-axis would be coming vertically through that page. Okay. So over here, this part of the graph is the positive x-axis, and this part is the positive y-axis. So this area that I'm outlining here would be the first quadrant of the xy plane. So just to kind of give you some perspective on what we're looking at here, and then this vertical axis running through our page here is the z-axis. Okay. So what we're going to do is we're going to plot this point that's an ordered triple. Okay, x coordinate of 6, y coordinate of -4, and z coordinate of 3.5. Now normally we know if we had just a xy coordinate, we would have 6, -4, we would go to 6 on the x-axis and then go down 4 units from there to -4 on the y-axis. So we still use those same principles. When the x coordinate is 6, we travel along the x-axis to 6, and then we head in the y direction, in this case the negative y direction. And you'll notice in the animation we're going to run parallel to these axes. Okay, so let me go ahead and click this here and let's see what happens. So here we are going to the x coordinate of 6, and now we're traveling along the y-axis to a value of -4, and then we're going to go up on the z-axis to 3.5. And that point, that red dot, is where the point, the ordered triple, 6, -4, 3.5 resides in space. Okay, relative to the origin. And you can see the rectangular shape that we kind of use to outline. That's kind of how we illustrate and show the dimension of the point relative to the axes in the origin. Okay, so kind of interesting here. Let me so let me do this again for you here so you can get a good idea of what's going on. So here we are. Let's reset it. Let's drop our y-axis flat to change our perspective. And let's go ahead and plot x, y, z. Now what I'm going to try to do is I'm going to try to pause after we plot the x and the y coordinate so you can get a little bit of a perspective here. So okay, so I went up a little bit, but before this red point started to go up a little bit, where we were in the xy plane, just that part of the space, is we were at the point 6, -4. Okay, so we went to 6 on the x-axis, and then we went to -4. And normally on the graph, on the normal xy plane, we would go over to the right 6, and we would go down to -4, right? So we're still going down, if you will, but it doesn't look down on our page, but we're going to the value that has a y value of -4. And then from there, we go and incorporate our z coordinate and get that third dimension in there. So that red dot is a point that's in space. And like I said, the rectangular outline that they give us, the rectangular prism shape that you see, gives us some reference, where that point is in space relative to the axes and the origin. Okay, so hopefully you find that fairly cool. I think it's pretty cool. I love three-dimensional graphing and three-dimensional space because really that's the world that we live in, and it's much more interesting. So okay, so we can use the elimination and substitution methods to solve a system of 3 equations and 3 variables by working with the equations in pairs. You will use one of the equations twice. When one point represents the solution of a system of equations in 3 variables, write it as an ordered triple, x, y, z. So what is the solution of the system? Use elimination. So here's our system over here, 3 equations. The equations are numbered to make the procedure easy to follow. Because as you can see, there's a fair amount of work to do here. But it's not, it's not awful to do. We just have to be very organized and meticulous as we're going through this process of solving this system. Okay. So you can see we have our three equations. We label them 1, 2, and 3, and we are going to work with them in pairs. So step 1 says to pair the equations to eliminate z. Then you will have two equations in x and y. So the first thing we do is we take 1 and 2 and pair them together and just solve that pair of equations, that system. And the reason we choose that is because we have a positive z and a negative z, so the elimination is already set up to take place. So we will go ahead and add those two equations together, and we will get 3x plus 2y equals 15. And we're going to call that new equation, we're going to call that number 4. Okay, over here, we've got 2 and 3. We're working with equations 2 and 3. And we're going to subtract the second equation from the first equation here. So there's a subtraction here. And what we get x minus 4x, which is negative 3x. 3y minus y is 2y. And negative z minus negative z, which is really negative z plus z, those are eliminated. So we get a 0. So when we subtract those, we get equation number 5, a new equation, negative 3x plus 2y equals negative 3. Okay, so what we've done here with these two equations, here and here, is we've combined two different pairs of equations together in a way that we eliminate the variable z. So now what we've done is we've basically created a two-variable, two-equation system that we know how to solve. So we'll write our new system using 4 and 5, and we will solve for x and y. Now, as you can see, it's nice here. These two equations, we can solve them by elimination because they're already set up for x to be eliminated. So we will just add the y's together, 4y. Add here, we get 15 plus negative 3, which is 12. So y equals 3 after we divide by 4. So here is our first coordinate that we know. Y is 3. Once we know y, we can go back, just like we would do in a two-variable system, and we can solve for x. So pick one of the equations, substitute 3 in for y, and solve for x. So that's this right here, and we get a value of 3 for x. So we have two of our values in our ordered triple, and the last step is to just solve for z. So we can go back to one of our original equations, and you can see here we've used number 1, plug in our value of x, which is 3, plug in our value of y, which is also 3, and solve this equation. And when we do that, we get z equals 1. So there's our z value. So we have a value of x, we have a value of y, and we have a value of z. So the solution to the system is the ordered triple 3, 3, 1. Okay? So as you can see, it's not, the math that we have to do is not terribly complicated. We just have to have an organized procedural way that we go about doing this, keeping track of what equations we're using. And like I said, it's very beneficial if you number the equations. Every time you get a new equation, just go ahead and number it until we get to the point where we're actually solving two equations and two variables. We are more familiar with those. So, okay, so what I want to show you, we're not going to use a graphical method to solve this system just because it's so involved, but what I do want to show you is I just want to show you what this does in fact look like graphically. Okay, it's actually kind of cool. Okay, so what I'm going to show you here is the graphical representation of the example that we just looked at. Just to show you guys what it looks like in space, what the intersection of the planes looks like in space. So here I have my what looks like XY axis, but really I've got a three-dimensional graph opened up here. So what I'm going to do is I'm just going to kind of turn this a little bit to give you guys some perspective. So here we go. So if I just take my finger on my app here that I have, if you kind of check out what I'm doing here, you can see here I've got my x-axis, I've got my y-axis, which is green, my x-axis is red, my z-axis is blue. Okay? So to the right of the intersection there would be the positive x-axis. The green above the intersection of the three axes would be the positive y-axis. And then kind of coming towards you from that intersection on the z-axis, that would be the positive z-axis. And the opposites would be those negative parts of the axis. So let me just kind of spin this around a little bit and you can kind of see what's going on here. with this cube just kind of outlines the graph space. So just like when you have a square graph space on your paper, here is a cube graph space in 3 dimensions. Okay, so here we have our space. Now what I'm going to do is, like I said, I'm going to kind of show you what the graph looks like here of our 3 equations. So our first equation was 2x minus y plus z equals 4. Okay, now that equation, its graph is a plane. So let me place that in here. All right, now let me turn this around so you can kind of see what it looks like. And you can see this flat surface. You can see that it's intersecting the y-axis at a point, it's intersecting the x-axis at a point, and it's also intersecting the z-axis at a point. So depending on how I turn this and spin this, you can kind of see where it's hitting each one of those axes, okay? So there's our first equation. Now, our second equation, which was x plus 3y minus z equals 11, is going to be a red plane. Let me insert that in here. All right, and there is our second equation. So now you can see where that red plane is intersecting the y-axis. It's also intersecting the x-axis, and it's intersecting the z-axis as well. And you can also see that the red plane and the blue plane are intersecting each other in a line. Okay? So we can see that's what the intersection of these 2 planes looks like. Okay? So if we were just looking with those 2 equations, the solution to the system of those 2 equations would be the line where those 2 planes intersect. But we have a third plane that we need to look at, and I'm going to put this on here, and it's going to be a green plane, and the equation for that was 4x plus y minus z equals 14. So let me insert this. And here is our green plane. Okay. So here we have our green plane. Now we have our green plane, we have our red plane, and we have our blue plane. Now, we know from our example that there is a solution to this system, and it's a single point. Okay, so as I rotate this around, you can kind of get an idea of where that point is. Okay, if I, right here where the polygonal looking parts of these planes intersect kind of in the middle there, that point is the intersection of the 3 planes. That's the only point in space that is on all 3 planes at the same time. Okay, and like I said here, depending on, you turn it around, you can see it. Okay, those 3 planes intersecting at that one distinct point. So anyway, I just did this on an app on my iPad. A very cool app. 3 dimensions. If you guys go beyond, into college and get into some engineering or some other mathematical fields, you'll get into 3-dimensional spaces a lot more. So here's just a couple different looks. Here's more of like a, more of a kind of a see-through look. You can kind of see the whole space a little bit. So again, just to kind of give you some perspective on what we're talking about here. But 3-dimensional graphing and 3-dimensional mathematics is very, very cool. Okay, so here's another example. What is the solution of the system? Use elimination. So here's another worked out example. You can see we have our 3 equations here numbered 1, 2, and 3. And you can see here that originally, if we choose 1 and 2 to use, we have to change one of the equations a little bit to make the elimination take place. So we're eliminating y. So we do that and get equation 4. Then we use equations 2 and 3. And again, if we eliminate y in the first pair, we have to eliminate y in the second pair. Okay, so we eliminate y, make the change that we need to make. We multiply the first equation by 2. We get this new equation, combine them into a new equation that doesn't have y in it again. And we'll call that 5. And then we'll take 4 and 5 that has x and z in them. And we will make a change to 4, multiply everything by -3. We'll combine it with 5, and we'll get an equation that just has z. We'll solve for z. We'll take that z value, go back and plug it into this fairly simple equation, solve for x. X is 1. If x is 1 and z is 3, we can substitute those values into one of our original equations and solve for y. Y equals -4. Okay, so the solution to this system would be 1, -4, 3. And here they're showing that we could check our work, which it's always a good idea to check your work if we have time. And if we don't have time, then maybe we can try to make time. Okay, folks, so we've had a couple of examples. You've maybe learned something about what it means to, or what it looks like to graph in three-dimensional space. And, we're not going to do a whole lot with three variable equations in 3D space, but this kind of gives you an idea of what we could possibly do. And there is some application of this, and you'll get to that in some of your assignments. So I hope you guys have a great day, and we will see you next time.